Our next speaker, Svilen Ivanov, is a software engineer at Smule with a couple of decades of experience, which means we should probably listen very carefully at what he has to say. And the topic is quite interesting. It's about service reliability and how failure is always an option. So please, big round of applause for Svilen.
Thank you, everybody. I hope you had a satisfying lunch, and I will try not to make you sleep today. So, I'm going to talk about service reliability engineering today, and the tagline of my talk is borrowed and adapted from the popular TV show called Mythbusters, where they are crushing things and they are learning from these crashes along the way and having fun. I hope we are going to do the same, having fun part. So, a few words about me. So, who am I? I can describe myself as a curious software engineer. I started my software development on an Apple II clone, and I started writing programs in BASIC. But BASIC was not fast enough, so I went to assembler for 6502 processor, and then I discovered that if I want to write games, I have to have joysticks, and I discovered that I don't have the necessary peripherals on my computer, so I had to solder a few chips on the motherboard of my computer in order to get joysticks working. So as you can see, my curiosity goes deeply into the stack until I find the reason about how the things are working. To quote Liam Neeson from the cheesy movie Taken, I have a very particular set of skills I have acquired over my career. As you can see here, he is probably taking an on-call call, and he is upset because there's something wrong in production, and he is about to fix it, probably by breaking a few bones here and there. So I joined Smule, my current company, 6 years ago. They successfully tested the idea that this small device that you are used to making phone calls in your pocket can actually be used for something else, something you can use and create music and express yourselves, not just taking phone calls and playing Snake. They were at this period, as every San Francisco-based startup, were using Ruby on Rails, because this is how you start a company in 2008. And they have experiencing some growing pains, which means that if we send a push notification back then to all our customers, we were not sure if our infrastructure will survive those clients that return. And when I joined, we started overhauling our infrastructure in order to make it more robust and more scalable. So what is Smule? So we are building this collaborative singing application, which means it's a sort of a karaoke app, but instead of singing karaoke into a limited audience in a bar or at a friend's house, you can sing with the entire world. It can be either turn-based, basically you can record one verse, someone else could record the other verse, both of you can record the chorus, and our software will combine this into an audio track or into a music video. Or it could be a real-time application. Think of it as a chat room, a video chat room, but instead of chatting, people are singing there. And it's community-driven. You can create your own rendition of a certain song, and you can upload it so people can sing over it. So a few stats about our ecosystem. Currently, we have around 50 million active users, which sing around 20 million songs per day, and they upload about 20 terabytes of data in a typical day. The storage is around a two-digit number of petabytes. That's one magnitude over terabyte. And on a typical day, we handle around 2,000 requests per second. Those requests are served by 3 geographically distributed data centers. And all these numbers serve one mission, to connect the world through music. So how do you make changes to a production environment like this. Let's use this car analogy. So you go to the auto repair shop and you want to change the tires of your car, but you stop using your car, you go there, it goes on this nice platform, all the tires are available and you can start changing them, everything is fine, you change all the tires and you continue your journey. However, the reality is a little bit different. As you can see, this is our current system at the moment. It is designed to handle 2x of our current load, so it can run only on 2 wheels. The people that are trying to change the tires is our ops team and our development team. Soon you are going to see them very happy because they are doing this change while the production is running. No one is noticing that we are actually doing some changes. And that looks like a little bit risky, don't you think? Yeah, they're about to change the tire. They will be very happy about it. Yeah, here it is. The tire, yay! So yeah, they do that. And we successfully deployed a patch and we can continue our journey. So let's deconstruct the title. So let's see how we can make this kind of risky operation more contained, a little less risky. So let's deconstruct the title. So what's the service? Service is the value that you provide the people. This is why they prefer to stare at their phones or visiting your app instead of doing something else. So it's a great privilege and it should not be taken for granted. It could be a website, it could be an application. Originally, the term SRE stood for Site Reliability Engineering, and it was coined by Google because their main product was their website, their search engine. I took the liberty to slightly modify it in order to be more broader, to be Service Reliability Engineering. Reliability is pretty self-explanatory and intuitive definition. You should keep your service running. Some people say that it's the most important feature of your service. I'm a little bit modest. I would say it's one of the most important features of your service. To rephrase this popular saying about the tree that falls in the forest and no one's there to hear it, does it matter how awesome your app is if there is no one who can use it? And the last part, engineering, is how we can achieve this service reliability by using our software engineering skills. We hate repetitive work. We don't want to do toil. We want to automate certain things, so we have these software engineering skills under our belt, which we can use. So let's get to know the enemy. What decreases the reliability? It's the complexity. First, let's start with the complexity and dependencies. The more complex a system is, the less reliable it is. Every component in your software system has a specific percentage of reliability. They're rarely 100%. And when you associate them in a dependency graph, that reliability decreases. Another source of decreased reliability is changes. Our software does not remain unchanged during its life cycle. We always want to make improvements, add more features, and as a result, every time we do a change, we decrease the reliability. And last but not least, in terms of priority, is the project age. Project age is something that directly correlates with the code size. So the larger the project is, the more bugs there are in it. And the bigger project you have, it's less reliable. So, can you achieve 100% reliability? Yes. To quote one contemporary poet, Mr. Marshall Mathers III, which usually goes by the alias Eminem, if you have one shot, one opportunity, would you seize it or let it slip? So, back then, in the late 70s, actually late 60s, early 70s, NASA noticed that the giants in our outer solar system will align in a way that if they send one single probe they will be able to visit all these giants. These are Jupiter, Saturn, Saturn's moon Titan, or Neptune. So what they did is they had to create 100% reliable software. And how they did it? They threw $1 billion at it. Yes, you can achieve 100% reliability, but it's very, very expensive. And it's probably not needed. For example, if you're developing a software for a pacemaker, that small device that keeps your heart running if you have a disease, if it has even 5/9 of reliability, that doesn't cut it. In that remaining 0.1%, if it stops, you're dead. So in these kind of applications, you do need 100% reliability. But in most of the cases, you don't. And it actually contradicts with other requirements. For example, you want to do a faster feature development. You can't freeze your production environment for the sake of reliability, because soon it will be outdated and your competitors will surpass you. And as a result, failures are inevitable. That's a very grim picture I painted here. So let's see, what are the failures? What can go wrong? Everything can go wrong. Computers are inherently unreliable. Resources are finite. You can easily exceed the resources of your available resources that you have, like CPU, memory, number of servers. Computers tend to fail. They have moving parts. They can be struck by a solar flare. Fortunately, we are not in such period, but it's also possible to happen. Have you guys read the Bible? I don't mean that one that was written by a crowdsourcing effort, but this one. So it's Steve McConnell's Bible, Code Complete. So there is a quote in this book which says there are X amount of errors in Y lines of delivered code. I deliberately removed the actual numbers because these numbers are from the late 90s. They might not be exact in 2018. But in general, X and Y are positive numbers. So you will have bugs in your code, no matter how good programmer you are or how great QA team you have. Eventually, bugs keep lurking in your code, and they will manifest themselves. So what you can do about it? Let's start with the basics. You can do monitoring. And what I mean by monitoring, I mean monitor everything. Let's start from the ground up, from the hardware. You can monitor temperature. It means that you have to record the temperature values over time. Parameters that the hard drive monitoring system gives you, like smart, power consumption, etc., etc. You can have all these parameters logged for every minute or for a specific period. Then you move up in the stack. So you can record operating system statistics, like CPU memory, network throughput, context switches, etc. Again, you log these values and you store them. Moving up on the stack, runtime environment statistics. For example, our code runs on JVM, and JVM provides a very comprehensive kind of flight recorder type of information, like a lot of telemetrics. Like, for example, number of running threads, how much memory your application is using, are there any threads that are currently blocked by some resource, etc. And you can get these values and export it out of that system. And finally, it's your application statistics. For example, they are very custom for your application. I'm going to give some examples. For example, API performance, request rates, total hits, depending what kind of application you're developing. And once you have this data, you have to grasp it. You have to understand what it represents. People brains are not very capable of comprehending a data if it's represented in numerical form. So you can use something to visualize it. The easiest way to visualize that data is to produce a simple line chart. Basically, the value that you have recorded over time. This way, you can see when it's high, when it's low, by just glancing over it. For other types of data, you can use different visualization methods. For example, you can use maps in order to represent the most popular location where your service is used. Or you can use color coding, like in a form of a heat map, where maximum values are red, minimum values are blue, and anything in between is some shade of these two colors. And you can visually see if your system is operating within the nominal capacity, or it's underutilized, or it's overutilized. Once you have this data plotted on a chart, it's one very important thing that we discovered is that data is not random. It depends on your users, how they are using your app. And you will start noticing periodicity, which can be also called seasonality. What seasonality means? For example, if you're developing a business application, you would expect that your customers will be visiting your application during the normal hours of your target country. So if it's Bulgaria, so you will see a spike of users during the business hours and not so many users during the nighttime. If you compare the data between today and yesterday, and you see a drop of your metrics, then there's probably something wrong with your system. Similarly, if you're developing a streaming application, which is streaming movies, you would expect that your users are going to watch movies during the weekend, during your free time, their free time, for example, in the evenings. And if you start seeing a decrease of throughput or the decrease of bandwidth that your application is serving during these periods, yesterday it was, let's say, 10 gigabits. Today it's just 5 gigabits. There is something wrong, and you can use this as a clues. And one thing that was very interesting, we started to grow internationally, and a few years ago we noticed a significant drop in our core metrics. So we started looking into our system, what we did wrong in order to cause this drop. When we have all the data, and we were able to drill down this data by country. So what we noticed is that we see a significant drop of certain Muslim countries. And why is that? It happened to be the month of Ramadan. Ramadan is a Muslim holiday which people usually fast. They don't drink and eat food during the day. And apparently, they also limit their application usage. So that drop was explained by an international holiday. And don't trust your internal system. Always have something to compare with. You can use an external service to validate that your service is accessible from around the world. Internet is very complex infrastructure, and if you are able to access something from Bulgaria, doesn't mean that it can be accessed as fast or at all from, let's say, Indonesia or Australia. Certain services allow you to validate your service availability without having presence in all these countries. And finally, which is very, which might seem unrelated to our technical monitoring, is listen to your customers. In our case, we're developing a music app. It doesn't mean that we have to listen to every performance that they are creating. But we are listening, we are monitoring the number of help desk requests we get for a given period. If we see an increase of help desk requests, then there is definitely something wrong. We also have ambassadors in certain social networks. They have these communities, sub-communities they have created on other social networks. So we have our ambassadors, which these are power users. These are not ambassadors in the legal term, but they are our power users, which can notify us if they see something that people are complaining over and over again. And of course, App Store reviews, that's very specific. If you have an application, that's also a very useful metric to see if your application is running properly. So what we do to achieve these monitoring goals? We initially started with a tool called Cacti, which had this very neat feature. You can create graphs by using a user interface, graphical user interface, browser-based, but it didn't cut it for us. The reason is that someone has to go there and actually click all this stuff every time we add a new server. And at some point, we started to experience scaling issues with that, so we decided to build our own monitoring system, which we called SMG. SMG is creatively named Smule Grapher. So it collects all the stats from all the servers that we have. It's built with Scala and runs on Play 2 framework and uses the excellent RRD tool for graphing. It's configuration-based. This is the part which we didn't like the most. Someone had to click and configure all these graphs manually or go deep into the Cacti implementation. So it integrates with Chef, so we can generate configurations for any server that we provision, and that, depending on the role of that server, if it's an application server or a web server or a database server, we have predefined templates, what kind of graphs that we want to have and what kind of values we want to monitor. It provides aggregated views. Basically, you can watch multiple servers as one, and the values will be aggregated, summed, averaged, grouped, etc. It's extensible via plugins. You can chart graphs using JavaScript charting library, not just RRT2, which produces plain old images. We also have a plugin for alerting. It's scalable, battle tested. We use it for over 3 years so far, and it's open source. It's available on GitHub, and you can take a look. There are live demo there, which you can use to see what it's like. So now, once you have all this data here, so what you're going to do? You're going to project this data, these charts, on a giant wall, and watch every graph that you have. That's certainly doable, but not very fun. So what you have to do is you have to set up a threshold. Threshold is basically a value which exceeded for a given period. That's very important. You should not. You should always define this value for a given period. For example, if number of requests exceed certain value within the current minute or a sliding window of a minute. So if that threshold is exceeded, you send an alert. Basically notify the team that something is going on here. And as yesterday, someone mentioned, not all alerts are born equal. Some alerts are more equal than others. So for example, you have to categorize your alerts. Informative and warnings can easily go over email, and you can review them once a day, maybe a couple of times a week. But others that require your immediate attention. Some critical service is down, you're running out of space on a very important server. So those should go directly to your mobile phone, either via text message, phone call, or a push notification through some third-party service. And the most important thing about the critical alerts is that they must be actionable. No one wants to receive an alert, pick the phone, something broke, and put the phone back in their pockets. They have to be actionable. When you receive that alert, you have to be sure that you have to take an action. You have to restart the service, deploy more servers, or do something else. Otherwise, people develop this alert fatigue. Basically, they get used to these alerts and stop paying attention. And that's very important because the important part is paying attention. It's very important because you may easily omit an alert which is critical for your infrastructure. And finally, if you have the chance to balance the on-call schedule, no one wants to be waken up in the middle of the night in order to fix a problem. So if you have the ability to use a globally, geographically distributed team, you can take advantage of it. The person who is sleepy, tired in the middle of the night may cause even more problems because of he is tired and sleepy than your current problem that you are trying to fix. So if you have a person on the other side of the globe, which is a normal day for him, maybe that person is more suitable for this task. Ewan yesterday mentioned briefly what to do during the incidents. I will only mention that during an incident, you should focus on bringing the service up again, to emphasize on that, and look for the root cause a little bit later. And the best place to look for the root cause is to write a postmortem. Postmortems were mentioned a few times. I will spend some time to describe them more, to describe them a little bit more. So it's a document, basically a written document that describes the incident. Sure, we can use email for that, but someone who wants to get the full picture has to read every email in a thread in order to get that full picture. If you summarize the incident into a document, he has to read a lot less. It should be written shortly after the storm is over. Basically, after you put up the fire, your service is running. Not the best solution that you did, but at least it's running. You have failover or did a quick fix. And then you have all the time you need in order to analyze what went wrong. And finally, it should be blameless. It means avoid finger pointing. Some companies have this culture where you should not adopt. You should not say, this person developed that feature and that feature didn't work, that's why production is down. Or that team did not do something properly, and that's why the database is gone. So it should be blameless. It's collective ownership of the problem, and it should be solved as a team, not to blame the problem on someone else. I'm going to quickly outline what a postmortem contains. It has owner and collaborators. Those are the people involved in the incident, but you can get help from other teams as well if needed. It has to have this executive incident summary, less technical details, but capturing the essence of the problem. It should have a timeline. When the problem was noticed, when someone reacted, how, when, and what they did, and when the incident was completed. That timeline is very important in order to track the mean time between recoveries. Basically, you want to try to make this time as short as possible. And if you have a very long timeline of a problem, you can probably improve on that. When you're not pressed of hundreds of an alert and you have time to reflect on the problem, you can start digging for the root cause. Very often, the incidents are caused by side effects of a root cause. The alerts that you're seeing are not usually reflecting what actually went wrong. And looking for the root cause is a very challenging task. And you should take your time to find what actually caused that. For example, your API started responding very slowly for no reason at all. And what you can see is that particular server is overheating and the operating system is throttling down the CPU in order to keep it from disintegrating, and that's why your service is slow. As you can see, the symptom, service is slow, has the root cause, overheating. What's the impact? It can be expressed as how many users of your service were impacted. Ideally, it should be as less as possible, but sometimes the impact is 100%, your system is down. Or you can use a monetary value. This is a very good indication. For example, you know that, let's say, you make $100 per hour, and if your service is down for 24 hours, you can calculate how much money you've lost. That's a very powerful indicator. What worked and what went wrong? That's kind of obvious. And the final, but the most important part is why you do that post-mortem. You should end with action items. What you can do to prevent this incident from happening again. It can be tickets, it can be change in a procedure, it can be expressed in all different in many different ways, but you have to have action items. Otherwise, that postmortem does not have any value. And finally, I'm going to end with something called error budgets. That term is coined by Google in their site reliability engineering book. It has a very interesting concept, which we are currently not doing, but we are evaluating it. So that concept is trying to solve this problem between developers and operational employees, ops. So developers say, oh, I have this very cool feature. It's very nice. It's super, super cool. People will love it. And you say, well, let's keep the system running for the next 6 months. You see, it's very, very stable so far. Let's not do any changes. So these are kind of conflicting agendas between the two teams. And the error budget concept allows you to combine these contradicting agendas into a common goal. So what you can do is you can define a service level indicator. This enterprisey sounding words mean you can use some objective metric to measure how well your application is performing. It could be uptime, error rate, performance. For example, how many requests you are under 100 milliseconds out of the all requests that you're serving. Now, then you take this service level indicator and you create a service level objective. Basically, you agree with the business that your service will be 99.99% available. And the error budget is actually the service level 1 minus service level objective, which means that normally you have a room to make mistakes, but not more than 0.1%. And what you can do with that budget. As I mentioned in the beginning, the change is number one cause of the outages. So when you launch a new feature, you're going to do a big change. So the chance of an outage or decreasing of reliability increases. So what you can do is you can spend this budget on new features. And the rule is very simple. If you are over the budget, which means more than 0.01% of errors, slow API requests, or uptime, then you have to pause your feature development, stop introducing new features, hence bugs, into the system, and focus on improving the reliability. If you are below the budget, go away. Launch the feature into production. If that feature decreases the budget, then you stop, regroup, and focus on improving the reliability. As you can see, this way the development teams will have an incentive to keep the error budget as big as possible to develop more stable features, and ops are not concerned about having a new feature launch into production as long as it meets the service level objective as of now. So that's a very interesting concept. I have linked a very nice talk by Christoph Lang from Google. I strongly recommend to listen to it. It's a very nice talk. I also linked the Site Reliability Engineering book, a lot of great resources on the topic. I only scratched the surface here. And a link to our monitoring tool if you want to take a look at it. Thank you very much.
Thank you. We have time for questions, so let me see the hands. If there are any questions. Svilen. All right, yeah.
Hello. I was wondering if you had any thoughts on observability rather than monitoring, which is something that's come up over the last few years and started getting more popularity.
Would you repeat observability?
Observability.
What do you mean by observability?
So it's the idea of, rather than monitoring for specific things that you know might fail, gathering enough data to see what could possibly be going wrong elsewhere in the stack. I was just wondering if you had any.
Are you referring to cascading failures kind of stuff?
Yeah, it's sort of like trying to find problems that you don't even know exist yet, for example.
Unfortunately, no.
Ah, okay. No
So,
worries.
yeah. However, we have experienced a lot of, well, not a lot, but enough cascading failures, which we learned a lot from. So what we tried to avoid at a certain point is when there is a problem with a specific backend service, it should not bring down the entire production, but only the users who are actively using that service. So we decided to split our users into what we call swim lanes, basically separate the users into specific buckets. And if something goes wrong in a specific bucket, the other users in the other bucket are not affected by the issue.
All right. More questions? Just wait for the mic to go. Try again. Hello? Again?
Hi there. You said when joining the company, you did some fixes on that. How did you make your architecture more robust? That's my question.
So yeah, when I started, we were in process of changing the programming language from Ruby on Rails to Java, and we saw that for example, we can't handle a load on a single database server. So what we decided to go with having more than one database server to store the user data, and also we saw that we can use a more mature language than Ruby that's more performant, that could lower our cost. So Java is much more performant than Ruby stack that we used back then. So by having this migration, we improve the performance and, of course, the cost. The other thing is when you do an overhaul, you basically we started from ground up by slowly replacing the APIs with the new system. So what we have learned with the mistakes from the previous system, we try to avoid them in the new one.
Right.
So it was iterative process.
Two more questions, yeah. Okay.
Hey. Yeah, sure. Do you have any separation between the team that creates features and maybe other team or subpart of the team that finds failures or fixes them? Do you have any separation or any
I'm sorry, would you repeat the question again?
Yeah, sure. Do you have any separation between the team that develops features and a team that fixes bugs or maybe looks for bugs and failures?
So if I understand the question correctly, do we separate feature development versus bug fixing cycles?
Yeah.
In terms of software development?
And in terms of team?
In terms of?
Team.
So one thing that we try to avoid is doing two big changes at a time. So when you make less changes in phases, it's much more easier to contain the problem, react immediately, and, for example, roll back or continue with the next phase. So if you're launching a big feature, maybe focus on that feature, not to bug fixing or improving other areas. So the less changes that you roll out, the better.
All right, one more question. With the green thing. Anyone else? Anyone want to test if this is reliable? Come on. All right, then, a big round of applause for Svilen.